All right, this video is for AP Calculus, and we're going to be talking about a really key idea today called the Fundamental Theorem of Calculus. It's called that because it ties together a couple of different areas that seem like they wouldn't be connected, but are super important to be connected together. This was discovered independently by two different mathematicians at roughly the same time, Isaac Newton and Gottfried Leibniz, and they both claimed credit for this and fought for credit for this for years. But we're going to just focus on how we can use this. I'm going to try to give you an intuitive understanding of why it's working, and then we'll actually look at an example. Then we'll look at the formal proof of it, and then we'll look at other things you can do with this. We're going to continue this discussion in the next section on displacement and total distance traveled and various other aspects of the use of the fundamental theorem. All right, so the fundamental theorem of calculus. We start with two seemingly different ideas that happen to use the same notation. We first defined the antiderivative of a function, which we write as capital F of x. And our symbol for that is this integral sign, and then this integral. We're taking the antiderivative of, and then the differential dx. Right, so if we don't put numbers here, it represents the antiderivative of whatever this function is, the function whose derivative is this function. But we also use that integral sign for the area under the curve, right, which we investigated with Riemann sums. And if we have a number here, we're going from this lower x to this upper x, and we're finding the area under the curve. Okay, so to consider this, let's take a simple example from the real world. Let's say that this function that we're working with happens to be the velocity for a car, and it's traveling on a highway at a constant speed of 60 miles an hour. So if I were to just graph this as a constant function of 60, right, 60 here, then what would the area under the curve represent? Which is what we are doing here with the definite integral. Well, the area under the curve would be a rectangle. It would just be this height times this width, right? And that height would just be a constant value of 60, and the units for that would be miles per hour because it's a velocity of speed. And then this width here would be a change in time, accumulation of time, so that would be 1 hour, so 1 hour. So if I multiply those two things together, the hours units would cancel out, and you would be left with miles. So this area here represents 60, but the units would be miles, right? So the distance traveled would be that we had traveled a total of 60 miles on that highway in the time from 0 to 1. Okay, if we instead decided to go from t equals 0 to 2 hours, then that means this height would be 60, and this width would be 2 hours, so 60 miles per hour times 2 hours, the hours would cancel, and we would have an accumulated distance of 120 miles. So this area under this velocity curve represents the amount of accumulated miles that we've traveled in that time frame. So we just get this idea in our head that the area under this velocity curve is the total accumulated distance that's traveled. Okay, but we also know that the velocity function is the derivative of the distance function. So that velocity function is also the derivative of the distance. And therefore, if we take the antiderivative of both sides here, right, the antiderivative of the velocity function would give you the distance, and this would be the antiderivative of that velocity function. So the antiderivative of a velocity function, using that same integral symbol, produces a function for the distance traveled. Right? So we could write it this way, that the distance traveled is the antiderivative of the velocity. So the total distance traveled equals the antiderivative of the velocity. But the total distance traveled also equals the area under the velocity curve, right? So since the total distance traveled equals the area under the velocity curve, and the total distance traveled also equals the antiderivative of velocity, the transitive property says that if two things are equal to a third thing, they must be equal to each other. And therefore, the area under the velocity curve has to be equal to the antiderivative of the velocity. Right, so if I take an area under a velocity curve that goes from time 0 to some time t, wherever I want to stop, that has to be equal to the antiderivative of the velocity. Right, so let's say that I didn't want to start at time 0. What if I wanted to start at time 1 and then go to time 2 and find out how much area I've covered, how much distance I've covered in that time frame? What you could do is first do the antiderivative from 0 to 2 to the ending time, and that would give you the antiderivative of the velocity, except at time 2. So it would be the antiderivative of the velocity representing the amount that's covered from 0 to 2. So with a 2 plugged in. But then we could also take the area under the curve from 0 to 1, which would represent the antiderivative of the velocity, but with 1 as the time. And then if you took this area and you subtracted this area off, you would get the goal area, the area between 1 and 2. And so that means that in order to compute the amount of distance traveled from hour 1 to hour 2, we could take the antiderivative of the velocity and then plug in the 2 time and subtract a copy of the antiderivative of velocity with 1 plugged in. So the accumulated distance depends upon the finding the values of the antiderivative of the velocity. We only need to do that at the ends of the intervals. And that's not at all intuitive. It kind of makes sense here when you're talking about it with a constant velocity. But what Isaac Newton and Gottfried Leibniz realized is that there's a proof that we can show you later that says that that would be true regardless of what this velocity curve was. So it wouldn't have to just be a constant. If you wanted to find the accumulation of the distance traveled, then you could take this velocity curve regardless of shape, take the antiderivative of that and plug in the ending time, and take another copy of that antiderivative and plug in the starting time. So this is called the Fundamental Theorem of Calculus, and there's actually 2 parts. Most books label this part 2. In general, anytime you have any function, it doesn't have to be a velocity function. Let's just call it f of x. If you want to take the area under the curve from a to b, then the way you can compute that area, instead of having to fill this with rectangular shapes or geometry shapes or anything like that, you can take the antiderivative of this function and then take 2 copies of it and plug in the x value at the upper end of the interval into the first copy and the x value at the lower end of the interval into the second copy, and subtract the 2, and that will give you the area under the curve. So that is definitely not intuitively obvious, but what that does is it gives us a much better way to evaluate a definite integral or an area under the curve than having to fit in approximations using rectangles or other geometry. So that means if we want to evaluate this definite integral, what we're going to do is say, let's take the antiderivative of this function. So this is what this is saying. I'll just write the pattern. If we take the definite integral or the area under the curve from a to b of some function f of x, that is equal to the antiderivative function with the b plugged in minus the antiderivative function with the a plugged in. So this is the formula for the fundamental theorem of calculus. So first we have to calculate the antiderivative of this. And that antiderivative is 2x plus, antiderivative, not derivative. That is, we have a constant of 1. It's going to be add 1 to this to get 3 divided by 3. Plus, we have a constant 2, and then this would be x squared divided by 2, which would simplify to 1/3 x cubed plus x squared. Okay. And then typically we want to keep track of these numbers, this 2 and the 4. So what we traditionally do is we put that antiderivative into a box, and on the right-hand side we put the lower x value and the upper x value here. Okay, so that is this f function. But the fundamental theorem says we have to take 2 copies of that function. So what we're going to do next is we're going to replace each of these with this pattern. I'm going to write what this antiderivative is, but I'm going to leave a space to fill in whatever x is. So here's a copy, 1/3 times something cubed plus something squared. That's this antiderivative. And then I would subtract another copy of that same antiderivative, leaving a space to plug things in. And then in the left copy, I'm going to take the upper number here and plug that in here. So that means we're going to plug a 4 in for x there, and we'll plug this number in to the right copy, right? So this number goes in the left copy, this number goes in the right copy. And whatever that evaluates to, that is equivalently the area under the curve. And so it will be a number. It represents the area under this curve, and we can find this instead of calculating it in some other way. So let's just graph that real quickly, just to highlight what is going on here. If I graph this function, let's graph this function, x squared plus 2x, because this is such an important idea. If I graph this, I'm just going to go origin plus or minus 10 so I can get a rough idea of the graph. The graph looks like this. It's a parabola that looks like this, right? X, Y. And what we're saying is, if you go from 2 to 4, there is an area under this curve. Instead of filling this with rectangles and approximating it, whatever this number is, that is exactly the area of that curve. So this area under this curve is exactly this number. So this is our primary method for evaluating area under a curve. We take the antiderivative of this expression, which is called the integral. Typically, we will copy the boundaries here, and then we will take 2 copies, plug in the rightmost boundary into the first one, and then subtract the leftmost boundary. So if you have that idea, see if you can pause the video and try this one on the left or on the right, and then unpause and see if you got that right. Okay, here's how I would do this. We would take the antiderivative of x to the 5th, which is 1/6 x to the 6th, x to the 6th divided by 6. Usually we put that in a box so we have some place to write the numbers. And then we take 2 copies of that, so that's 1/6 something to the 6th minus another copy, 1/6 something to the 6th, and we plug in the 3 in this copy, and we plug in the -1 in this copy. Right, so that is the area under this curve, exactly right. So that's the main application for the fundamental theorem of calculus. Okay, this is so important. I think we should take a quick look at the proof. Normally we wouldn't do that in the video, but I think it's worth taking a quick look. So let's look real quickly. If a function f is continuous on the closed interval from a to b, and capital F is the antiderivative of f on the interval from a to b, then the definite integral from a to b of f of x is equal to the antiderivative with the b plugged in minus the antiderivative of the a. Notice there's no restriction on what f can be as long as it is continuous everywhere in the interval. That is a condition that needs to be met. And we'll look at what happens when that's not true towards the end of the unit here. So proof, let delta be any partition of this domain from a to b, where these are in order from x0, x1, and so on, covering n x's, arbitrary placement between a and b. The right-hand side of this expression here can be replaced with the endpoint values along with values between these values. So we're going to start with the right-hand side. This is fb minus fa, where this is the antiderivative. But then we're going to say, since that's true, we can add and subtract any number of intermediate values here. So we can say that this ends, b is the nth x, x0 is the starting x. So this fb gets replaced with f of x n. This f of a gets replaced with f of x0, and in between we can pick any other x's, and we can just subtract and add the exact same f's in pairs like that. Then we can regroup them so that we can say this x to the n1 can be regrouped with this first pair. So f of x n minus f of x to the n minus 1. These can be paired together, and these can be paired together, and so on. So we group them up in this way. And so then we can say that this is really a summation. It's a summation of n little intervals in x, and in each case, this right-hand side is a sum of the f on the right side minus the f on the left side of that little interval. Okay, now by the mean value theorem, we know that as long as the function is continuous over the interval, we know there has to exist a c between this x and this x for any interval, such that the derivative at that value is equal to the average rate of change of the y variable over that, which is the change in y over the change in x in that interval. And therefore, we could solve for this by multiplying both sides by this expression here. So this difference here from the f on the right side to f on the left side is equal to the derivative at some intermediate x in that interval times the width of the interval. Right? And because the capital F is an antiderivative of f, that means the derivative of that would be the original f function at that value. And if we rename this change in x over an interval as delta xi, that means you can replace this with delta xi, and you can replace this derivative of the antiderivative with the original function. So that's the right-hand side. So from earlier, we said the right-hand side of the theorem is equal to this summation. And then that means we're replacing this now with f of c delta x. That tells us that by repeatedly applying the mean value theorem, you can always find a collection of fc's such that that constant is a Riemann sum. If you then just take the limit as n approaches infinity of those rectangles and make the rectangles infinitely small, this is the exact structure that we've defined as the definite integral. It's the integral from the starting a to the ending b. This f becomes that, this becomes the differential, and therefore we can show that it's true that that is equal to the antiderivative, and we only have to plug in the two ends. That's because they're adding and subtracting all the intermediate values. So that's what allows this to work for any shape function. It doesn't just have to be like a constant velocity function. So an interesting proof that relies on the mean value theorem. Okay, let's go ahead then and just take a look at a few more examples of this. Number 3, we've got g of x is an integral from 2 to x of t squared t. So sometimes we might want to put variables in the limits of integration here, these boundaries, in which case we have to use a different letter here. So that's fine, we can do that. So if I wanted to evaluate that, I could just do what this says. We're going to take the antiderivative of t squared, which would be 1/3 t cubed. And then we're going to plug in a 2 here and an x here, which means we're going to take 2 copies of these antiderivatives. There's the antiderivative, minus another copy of the antiderivative. And we're going to plug in an x into this one and a 2 into this one. Right, so this would be the expression that would give me that. And that means that there is a function now. This function, g of x, is 1/3 x cubed minus, this is 8/3. Okay. So what that's telling me is if I start at time 2, let's say t is time, and I end at some unknown time x, this will give me the area under the curve from 2 to that value x without specifying the x ahead of time. Sometimes this is referred to as an accumulation function, because it shows the accumulation of the area. Okay, and we could do the same thing over here. Let's do this just as stated. If we want to evaluate that, we're going to say definite integral requires us to take the antiderivative. So that would be 3. This would be t to the 4th over 4. And we're evaluating this starting at 3 and ending at wherever x squared is. We're leaving that as a variable so it can be changed at a later time. So it's going to be a copy 3/4 times something to the 4th minus another copy 3/4 times something to the 4th. And we're going to plug in the x squared here, and we're going to plug in the 3 here. So this g of x function would be 3/4, and then this is x to the squared to the 4th, and then minus 3/4, 3 to the 4th. Okay, so this is the accumulation function for that. All right, the reason I'm having us do that is because we might then ask, what if we did that function and we took the derivative of that result? So let's say we evaluate this and then we take the derivative. So I'm going to go through that same process again. G of x is the antiderivative here, which is 1/3 t cubed, evaluated from 2 to x. So g of x is equal to the 2 copies of the antiderivative function with an x plugged in here and a 2 plugged in here. And that gives me g of x is 1/3 x cubed minus 8/3. But then it's saying, now let's find the derivative of that, g prime. So g prime means we're going to take the derivative of this 1/3 x cubed minus 8/3. So the derivative here would be, we would bring this 3 back down, and it would be 1 times x squared, and the derivative of that constant is 0. So I want you to notice something here. In that case, if we look at what's going on here, I could just go straight to this. I could say, well, this g prime is equal to the derivative of this, which is 2 to the x t squared dt. But a derivative and an antiderivative should be undoing each other's effects. So that should just leave this t squared, right? So it should just leave something squared, right? And look at the result is x squared. It is simply this x plugged in here. So a faster way to do this, if I know that I have an integral defining a function, and then I need to take the derivative of the integral, is to recognize that the derivative and the integral cancel each other out, and this x simply gets plugged in to the remaining function, because the derivative of the integral just produces a variable something squared, and the x gets plugged in there. This is x squared. Does that work over here? Not quite the same. Let's do the same procedure that we just did. If you take the g of x, I'm going to take the antiderivative here, which is going to be 3/4 t to the 4th, plugging in 3 and x squared. And so that would be 2 copies, 3/4 something to the 4th, minus 3/4 something to the 4th, with an x squared plugged in here and a 3 plugged in here. And that's going to give me 3/4 x squared to the 4th minus a big constant here, which is 3/4 times 3 to the 4th. I won't bother to simplify that. Okay, but then if we want to take the derivative of that, g prime would be the derivative of this, 3/4 x squared to the 4th minus 3/4 3 to the 4th. So the derivative of this first term would be 3/4. Then we would bring the 4 down here, so 4 times x squared to the 3rd. But because this isn't just an x, we would have to multiply by 2x for the chain rule. This whole thing is a constant though, so the derivative of that would just be 0. So the result here is g prime of x is, these cancel and produce 3 times x squared cubed, but times the 2x. So could we do something simpler here, like we did over here, and recognize that the derivative cancels off the antiderivative? We can. G prime of x is equal to the derivative of this g of x, which is 3 to the x squared, 3t cubed dt. So what should happen is the derivative and the antiderivative are canceling, and that's going to just leave this function, 3 times something cubed. What I'm going to do is plug in this x squared into here, which is the x squared, but because that wasn't an x, I'm going to multiply by the derivative by the chain rule, and sure enough, that gives me the answer without having to go through all of this work. So the fundamental theorem also says that we can recognize that the derivative and the antiderivative are canceling each other's effects out. It's just that when we're taking a derivative of an integral, we're also taking a derivative, which means we have to be cognizant of if what we're plugging in is something other than x. Then we have to multiply by the derivative of that to have the chain rule work. All right. So this is sometimes known as part 1 of the fundamental theorem. If a function f is continuous on an open interval I containing then containing this constant, then for every x in the interval, the derivative of an integral from a constant to a variable is simply this function with the x plugged in. But you also have to be cognizant that if what you're plugging in is something other than x, you have to multiply by the derivative. Even more generally, if we wanted to see one last case before we kind of move on, let's look at this. I would say, although it's not usually written this way in the textbook, we should be writing it this way. The derivative of an integral from any constant to g of x, where that's a function, the derivative and the antiderivative cancel, and you just get this function, but you have the g of x plugged in. But if that's anything other than x, you have to multiply by the derivative. Most generally, what if this one wasn't a constant? What if they were both functions? Like maybe this is x squared and x to the fifth or something like that. Then you could just say that you're going to take the derivative and the antiderivative, cancel and leave f. So you just take f and plug in the top function times its derivative by the chain rule, and subtract the antiderivative with the bottom function plugged in and its derivative. Let me show you a quick example of that. Although we don't typically see this on the AP, let's say that you have this. The derivative of an integral that went from x squared to x cubed of, and I'll put a function in here. Let's say it is t squared. Okay. What this is saying is we can take the antiderivative, which is 2t, so I'm going to take 2 times something, and then I'm going to be plugging in x squared and x cubed into that. So instead of making it the antiderivative, I'm sorry, I shouldn't do that, right? I'm going to say this derivative and this antiderivative cancel, and they just leave the t squared. So something squared. In the first one, I'm going to plug in the x cubed times its derivative, which is 3x squared. And then I'm going to subtract another copy of that derivative of an integral, which is t squared, but with the x squared plugged in, times its derivative with a chain rule. Right? And if that's too confusing, you can always just actually do these as 2 separate steps. So let me show you that. But if that feels too confusing to you, you could say, let's just ignore this for a second and just do this. The antiderivative is 1/3 something cubed, right? T cubed. And I'm going to evaluate that from x squared to x cubed, which means I'm going to take 2 copies of this. So it's going to be 1/3 times something cubed minus 1/3 times something cubed. And we'll plug in the x cubed over here, and we'll plug in the x squared over here. Right? Then we will take the derivative of that result. So the derivative of that result is the derivative of this 1/3 x cubed minus 1/3 x squared cubed is, the derivative here is, when we bring this 3 down, it's 1 times that thing squared with x cubed plugged in, but by the chain rule, we have to multiply by the 3x squared. And you would subtract. Bringing this 3 down here, with the derivative, we get 1 times this squared with an x squared plugged in times its derivative, which is 2x. And that gives me the same thing that we got here. So this is just recognizing that you can say if you're taking a derivative of a function that's defined with an integral, the derivative is going to cancel the integral and give you that same structure. This is like t squared with something plugged in. Okay, let's see, how many examples do we have here? Okay, for the rest of this, we're not going to show any more topics, we're just going to show examples of these things being done. So you can try pausing the videos and see if you can get the answers before I'm pausing and checking. Okay, the way I would do this problem, we're taking a derivative of an integral, which means that they're going to cancel and just leave this exact function. So this is just whatever that function is with 3x to the 4th plugged in, but because we're ultimately taking the derivative, we have to multiply by the derivative 12x cubed minus the other copy, which is that same function. The derivative of the integral is f with x squared plugged in times the derivative of the inside. So this would be that. For this one, I could do this. I could say, you know what? Let's do this. For me to use that rule where I just plug in straight and ignore the constant needs to be in the bottom of this. So I'm going to do this first. The derivative of this, if I swap this and put the constant on the bottom, then that gives me the negative of the result that I would have. And then the derivative and the antiderivative are canceling, so that's negative. The derivative gives me this f, except with the x cubed plugged in, and I will multiply by the 3x squared. So you can just reverse these, because if you're going to use this form where you are plugging this in, the constant must be in the bottom. Let's just see why by working this the longer way. If we decided to do this the long way, you could do this integral first as is, and I'm not going to reverse these. So if I just did x cubed, I would just be finding the antiderivative of this. I don't know what it is, but I'm going to call it capital F, and I'm going to be plugging in x cubed and 2. So I would be taking the antiderivative of 2 plugged in and subtracting the antiderivative of x cubed plugged in. And then I would take that result, and I would take the derivative of that. So the derivative of this is some function with a constant plugged in, so that is a constant. And that means the derivative of that constant is 0. Then I would have minus the derivative of f is the original lowercase f. But because I'm taking the derivative, I multiply by 3x squared. And we get the same thing that we got up here. So you can either do it the long way, or you can just reverse these and make that negative, and then just plug this directly. And just remember that if what you're plugging in is more complicated than x, you have to multiply by the chain rule derivative. Okay, this says, find the interval on which the curve, or y, is concave up. All right, so remember, concave up happens when the second derivative is positive. So to do that, I'm going to have to take 2 derivatives here. So first, we can go ahead and take the first derivative, y prime, by saying that's equal to the derivative of the integral from 0 to x of 1 over 1 plus t squared dt. Okay, so the derivative and the integral cancel each other out. I have a constant here, and that just means that I'm going to get the same function except with x plugged in here. 1 plus x squared. So that's the derivative, the first derivative. Then we can take the second derivative. So I'm going to actually write this as 1 plus x squared to the negative 1 and use the power rule to take the second derivative. That's negative 1 plus x squared to the negative 2 times the derivative of the inside, which is 0 plus 1 plus 2x. So that's negative 1 plus 2x over 1 plus x squared squared. Okay, we're interested in finding the interval over where this curve is concave up. So we're interested in where is this greater than 0. Right? So, well, the bottom of this fraction is definitely positive. So for this to be positive, we have to have negative 1 plus 2x be greater than 0. Right? So, let's see. Negative 1 minus 2x greater than 0. We could distribute that. We could add 1 to both sides here in this inequality. Negative 2x is greater than positive 1. We could divide both sides by negative 2, which would be x, and this is negative 1/2. But remember, whenever you multiply or divide an inequality by a negative, you have to change the direction. So it looks like any x that is less than negative 1/2 will make this numerator positive, which will make this whole second derivative positive, which will mean that the function is concave upward. Okay, one last example. Let g be defined with this accumulation integral where the graph of f is shown. So this is a graph of f. First of all, evaluate g of 5. So what we can do for that is, for a, g of 5 is, we're just going to plug in 5 for x. So that means we're going to use this integral, but we're going to place that x with a 5. F of t dt. Okay. So that means I need to find some way to evaluate this. If I had an expression here, I can take the antiderivative and plug in 5 and 0. But instead, I'm going to have to approximate this or find this in some way with area under a curve. This also means the area under the curve from x is 0 here to 1, 2, 3, 4, 5. This is 5 right here. So we want the area under the curve. So it looks to me like we can use geometry to evaluate this. We've got a positive area there, which is 2. We have, let's see, a positive area there, which is 2. We have a positive area here, which is half of 2, so that's 1. And then we have a rectangle or a triangle here, which is half of this rectangle. There's 1, 2, 3, 4 units divided by half is 2. And then we also have some negative area down here. So this is a triangle that is let's see, 1, 2, 3, 4 divided by 2, that is a -2 area. This is a -2 area. And this is, let's see, this is an area of 2 cut in half -1. So what I'm going to do to evaluate this this area is I'm going to use, I'm going to evaluate this definite integral by filling the shape with geometry shapes. It's 2 plus 2 plus 1 plus 2. And then there's -2, -2, -1. So let's see, these 2's cancel, these 2's cancel, these 1's cancel, and it ends up being 2. So g of 5 is equal to 2. And then on one interval is g of x increasing. Okay, so for that, maybe we can just say this. G of x is increasing let's see, g of x is increasing where g prime of x is greater than 0, right? Can we analyze it that way? G prime of x is 0. Yeah, so let's do that. Let's figure out what the derivative is. G prime of x is going to be the derivative of this g of x, which is an integral from 0 to x of f of t dt. The derivative will cancel the integral, and since we have a constant here and a function here, this is just equal to f with the x plugged in. So I'm just looking for places where g prime of x is greater than 0. G prime of x is greater than 0, where f of x is greater than 0 because f of x is equal to g prime of x. And so looking at this function curve here of f, where is f of x greater than 0? F of x is greater than 0 whenever it's up here. So for this range in here, from x equals 0 to x equals 3, f of x is positive. We just have a positive f there. So we can say which occurs for x between 0 and 3. I'm going to put 0 on there because we do have a positive x there, but at 3 it's 0, so technically it's not greater than 0. And then we can say, where does g of x have a maximum value? And for that, we can say g of x will have a maximum value at wherever g prime of x is 0 at critical points, or it could be at interval n's. So we're going to do a candidates test here to evaluate where g of x has a maximum value, because effectively we're finding the max value over the interval from 0 to 3, 4, 5, 6, 7. All right, so what are the possible locations? Well, g prime of x, we said in part B, is equal to f of x, and that's equal to 0 at 3 and at 4, 5, 6, 7, at x equals 3 and x equals 7. So what we could do here is come up with some table here and say candidates for where x could be maximized at 3 and at 7. And we also have to consider the endpoints. So we already have 7 on there, but we also have to add 0 on there. And then we have to plug this into g, because we're trying to maximize g. But g of x is defined with this integral definition as the integral from 0 to x of f of t dt. So to evaluate this at 3, g of 3 is the integral from 0 to 3 of f of t, which means we have to find the area under the curve between 0 and 3. So let me go back to the method with the geometry things there. We've got some positive areas here. This is a positive 2 area here. This is a positive 2 area. This is 3 over here. This is a positive 1 area, and this is a positive 2 area here, because it's half of 4. So this would just be equal to 2 plus 2 plus 1 plus 2, which is 6 plus 1 is 7. Okay, so that is g of 3. Okay, we can also do the same sort of calculation for g of 7. So for g of 7, we're taking the integral from 0 to 7 of f of t. That means that we have all of that area, so that original 7, plus we have to add in this negative area. So there's a negative 2 for that region. There's a negative 2 for this region. And there's a negative 1 for that region. So that's 7 minus 2 is 5, minus 3 more is 2. And then finally, g of 0, they gave in the problem, or no, we evaluated that in part A to also be 2. So they asked me, where is this function maximum? So it's maximum here. We can say it this way: g of x has maximum value of 7 at x equals 3. We're really being asked about where the maximum occurs. And that makes sense, because as you're increasing x, the area keeps increasing and increasing until it gets to here. Once the function goes negative, the overall accumulated area starts to decrease. So it makes sense that this would be the location when the area is maximum. Okay, we're going to stop this video right there, and we'll move on to a related topic in the next video.